This is StarTalk, Cosmic Queries Edition. I'm your host, Neil deGrasse Tyson, your personal astrophysicist. And my guest co-host today is a friend of StarTalk, the one and only Paul Mecurio. Paul.
Hey, Neil, how are you?
Welcome back to StarTalk.
Nice to be back. Great to see you again.
Man, let me just remind people who you are. Like, you started out, was it an investment banker or something?
Yeah,
and that wasn't funny enough for you, so you became a comedian? What the hell happened there? And how much of a disappointment were you now to your family?
Then and now. I can't even say that I was a lawyer. I was
Sorry, I got it.
No, Bo, you got it right. I was doing M&A law, and I was like, okay.
Mergers and acquisitions. See, you're still in it. You see.
Right, no, sorry. Exactly. I was Gordon Gekko with big lips. And then I decided, well, I want to really sort of, be a little bit more scummy. So I'm going to be an investment banker. And then I
a lawyer defending investment bankers wasn't scummy enough for you.
Exactly. It's like, why am I defending these guys when I could be one of them and be making 4 times the money? And so I'm like, let me go jump ship. And I was still doing mergers and acquisitions, but on the banking side. And the difference is, like, the bankers sort of come up, do the financial modeling to decide the value of the company, and then they get into a price negotiation and they hand it off to the lawyers, and then we negotiated.
So you were already in how all that worked anyway. That's what it seems like.
Yeah. So if you got put out of a job because it was an M&A deal, just tweet me. You can. Here's my address if you want to come and burn my house down.
It might have been you.
It might have been me. And then I thought, how could I disappoint everybody in my life, including my wife? I know. I'll go into comedy and entertainment and start all over again. And then that's what I did.
No, I enjoyed your story. We had lunch recently, and you were telling me that part of the birth, the origin story of Paul Mecurio was selling a couple of handwritten jokes to Jay Leno for the Tonight Show. That's just, I love that. I love that. And now you do the warm up for Stephen Colbert. And the Late Show.
And the Late Show. I wrote on the Daily Show, worked on the Colbert Report, and now work on this show, and then appear on the Late Show occasionally too. And
so if I'm ever watching Stephen Colbert and his audience looks a little dead, it's because you failed.
No.
Because you're supposed to get them all excited, right?
No, it's because I wasn't there and some lame-o filled in for me.
Ooh, good one.
No, it's this weird sort of thing. You can't do jokes in it because it doesn't work in that setting. You need like an intimate space and
with cocktail tables kind of space. And then angry waitresses serving around you, that kind of thing. And then just to remind people that his show is in the Ed Sullivan Theater, so it's actually a theater, not just a little recording space, right?
Yeah, it's pretty incredible. I mean, you've been to the show, and I don't know if you saw downstairs, but below they have these huge timbers and an elephant painted on the wall, and it turns out that they used to have the Ringling Brothers Circus perform in the theater, and they would bring the elephants in on the 53rd Street entrance, and they needed to put these timbers up to support the stage because of the elephants. So,
but just to be clear, the Ringling Brothers came to perform at Madison Square Garden, not only on the Ed Sullivan Show. So this was like PR for the regular show, right?
Yeah,
you wouldn't go to the Ed Sullivan Show to watch a three-ring circus, right?
Exactly. Well, a couple of the elephants were divas. They wouldn't even go on the Sullivan Show. They're like, I don't need that. And they're just looking at their hooves like, what?
Do elephants have hooves? No, I don't think so.
I don't think so. They're large toes.
I'd call them big feet. That's really good.
I was starting to feel stupid when you corrected me. Then your answer didn't make me feel so stupid now. They have those big feet. So it's a compact thing, like in 10 or 15 minutes. You got to. It's a weird to go into a TV taping for an audience is strange because a lot of people haven't been before, so you don't really know. And I think sometimes they think you have to kind of actually be quiet and like polite, and we want the opposite.
Because otherwise you interfere with the filming, right? So
they think that
ethos.
Right, and the whole vibe is that they create this wave of energy, and then we kind of surf it. So, you've been on it. They love you. I mean, you've been heckled a couple of times, but we cut that out and edit. And I can't believe somebody threw a pie at you from the balcony. I thought that was highly inappropriate. It was something like, "You haven't returned my email in 3 years," and then he threw a pie at you. And I was like, "Wow, this guy's got a lot of enemies." No.
Well, I like
anyway.
reintroducing you to our audience, so
Yes.
it's great to get some
I
of that
appreciate
background. So did you come loaded with questions from our audience?
did.
And what's the theme today?
The theme is sort of a grab bag.
Grab bag? Okay, we have those every now and then.
Yeah, but there does seem to be a little bit of a through line of sort of, in terms of the galaxy and sort of measurements. But we'll jump in.
If I know the answer, I'll
I read through these ahead of time. I don't think you're going to know any of this, so I will.
So let's just end it here.
Yeah. Why don't you just have a glass of wine and I'll take over, Mr. Big Feet. And all right, so we'll get started then.
Yeah, let's do it. Let's do it.
Okay, I apologize on this first name. It's a little tricky, but I'll do my best here. It's Hede Wagamans, and the question is:
Do we know where Hede comes from?
We
I was like knowing their origin.
We do not know.
Okay.
I just have the name.
By the way, and
Patreon, I think.
Yeah. All these are Patreon, right? So Patreon, they get perks for supporting the show, and so we love them for that. And here we have it. So yeah. So what do you have?
If the universe expands at light speed, how does it expand at light speed? And by the way, I've listened to all of the episodes of StarTalk Radio. You don't have to kiss ass. You're going to get your answer here, okay? You don't need to. Ooh.
Well, at least he said it at the end of the question, right? Rather than
Exactly.
the beginning. Right. That shows a little more class.
Yeah, exactly. Let me slip it in. So yeah, if the universe expands at light speed, how does it expand at light speed?
Yeah, that's a common concern people have when they learn of this. And because they know fundamentally that nothing can travel faster than light. So how is it that the universe could possibly expand faster than light? In fact, if you go to the early universe, right after the Big Bang, it was expanding way faster than the speed of light. So here's where the rubber hits the road, or the spaceship hits the vacuum, or however that'll work.
That works.
So Einstein's in 1905, Einstein came out with his, quote, theory of relativity. But that theory of relativity was in a very restrictive case, okay? And so it came to be known as the special theory of relativity. Not because it was special, like you're special. No, it's not that. It's because it was a limited invocation of the principles of relativity. So it was a special case, really, is what it should have been called, really. And it would take him another 10 years to generalize the principles of relativity to a much larger, more encompassing concept. And that,
which by the way proves 10 years, he was lazy. Let's be honest.
You think what that is?
I could have done it in 2.
Lazy bum.
I could have done it in 2. Anyway, I didn't mean to interrupt.
So it became the special theory of relativity broadened to become the general theory of relativity. Okay, so that's what's going on there. And so it turns out in the special theory of relativity, it describes what happens when you move through a pre-existing space and time. And if you're trying to move through pre-existing space and time, there are speed limits. The speed of light. It's not just a good idea.
It's just, what happens, is it possible to exceed
But you
that
have to
speed
finish
limit?
the line. It's not just a good idea. It's the law. Don't you remember this?
I'm sorry.
What?
I missed it. I'm sorry. I missed it.
Have you been living in New York so long that you forgot how to drive and you forgot those rules about the speed limit?
Yeah, exactly. I totally missed it. Yes. Or it's not just a good idea. It's the law. Okay.
It's the law. You missed it. You know, I'm hanging these low hanging fruit for you.
I know.
Okay. So in the universe, so what's interesting is photons, packets of energy, do move at the speed of light. But anything with mass cannot ever achieve the speed of light under the tenets of the special theory of relativity. And what happens is the circumstances become oddly interesting, right? So if you're going to watch me move faster and faster and faster, you will see that my time will begin to slow down. You'll compare my clock to yours I'm on a spaceship and you're down here on Earth and you watch me fly by, my clock will tick slower than your clock. And not only that, you will see the length of my spaceship shorten in the direction I'm moving. And you will see that my mass has increased. And I will have no idea any of that is happening. So even though you see my spaceship getting shrunk front to back, I'm in the spaceship and I look behind me, I look in front of me, and it's a normal spaceship. So the point that Einstein noted, this is one tiny piece of his vast brilliance, is that while I'm on the spaceship, if I try to measure the length of the spaceship, my ruler shrinks as well. So I'll still measure the same length, even though you're going to say, hey, Neil, you're really shrunken up. I said, no, I haven't. And I take out my shrunken ruler and I say, everything is fine.
But is it the
okay, so here's what happened.
Shrinkage?
It's a great question. So what the reason, well, I don't want to call it the reason like that, like someone made this a reason. It is just the reality of the universe in which we live. And it's that everybody measures the same speed of light, no matter how fast you're going, right? So if you're on the front of a train, let's say a train's going 60 miles an hour, and then you throw a rock 10 miles an hour in front of you, okay? You're standing on the train and the rock is leaving you 10 miles an hour, okay? Someone on the ground will see the rock go 10 miles an hour plus the speed of the train, okay? So the train's going 60, they'll see the rock going 60, going 10, and so the rock 10 in front of the train is actually going 70 miles an hour. It adds for that person.
Okay. I was just thinking it would catch up, but it does.
No, it doesn't. No. Once you throw it, it'll fall. But if you just throw it out ahead, now watch. If I send a beam of light in front of me, I will measure it to have the speed of light. You, on the ground, try to measure that same beam of light, even though I beamed it in front of a train, and you will also get the exact same value for the speed of light. This is freaky.
Right.
The speed that you measure for light is independent of how fast you're moving. So Einstein said, how do I make that happen in the calculations? The only way we can all agree that the speed of light is the same, no matter who's measuring it, is if my length shrinks as I go by you, is if my mass increases, and if my time slows down. So that simple observation about the universe, that everybody measures the same speed of light, forces all the rest of that to be true. And that is the special theory of relativity. Okay, so now, 10 years goes by because he's just such a lazy bum, and then he figures out how to think about this with regard to accelerations. So not just how fast you're going, but suppose you're accelerating. Suppose there's the full answer to this question would take an hour, but I'm going to shorten it and say that the expanding universe is not an object moving within the pre-existing universe, and therefore the speed of light plays no role in constraining it.
So it can expand at any rate of speed?
Arbitrarily fast, because nothing is moving faster than light within the medium. So it is the stretching of the medium itself. And that was allowed in the general theory of relativity, which still constrains your speed if you're trying to move within the space itself.
And so if something can expand with no parameters, is it possible to measure that in any way?
No, what'll happen is as the universe, so you'll see a part of the universe expanding, and let's say it hits the speed of light. Well, the light it tries to send you will lose all energy before it reaches you, so it basically disappears, and it creates a horizon for you. And so that's what I'm saying. Yeah. So that's what's interesting. So there's more universe out there. It's just beyond the horizon, and that light will never reach you. Oh. Because the universe is expanding faster than the speed of light can come towards you. So yeah, it's gone forever. So you'll never even see objects embedded in space moving at the speed of light or greater.
So the short answer to if the universe expands, how does it expand at light speed? is very complicated. It's not sort of it's this or it's that. It just depends on the medium and the circumstances.
No, it depends if it's because the space is expanding, not
Right.
objects moving within the space at the speed of light. So that's
Right.
that's the fundamental difference there. Okay, and there's a really brilliant reason how and why Einstein came up with this concept of the general theory of relativity. It's the equivalence principle, and I could get into it if we have time, but we're going to have to take a break in like a minute. But I just want to say that the short answer here is general theory of relativity allows space to expand at arbitrary speeds, and it is not constrained by the speed of light. Whereas we are, because we're embedded in a pre-existing space-time,
Got it.
and we cannot then go faster than light.
Got it.
That's the difference.
Let me be clear. You all are. I am not constrained. I'm a whole other being that is able to morph. I'm the bad guy in Terminator.
There you go. There you go.
I'm
By the
liquid
way,
steel.
By the way, the Terminator 2, to get you, yeah, okay.
I hate it when you correct me and you're
No,
right.
I'm not actually correcting you. I'm just enhancing the truth of what you're saying.
Nice. Wow, you must be fun to get in an argument with your wife. Honey, I'm not correcting you. I'm enhancing you. Well, enhance outside because you're not sleeping in this bed tonight.
So, so science fiction authors know all about this limit of the speed of light, and they don't want to violate that. All right, it's like sacrosanct. So what they do is they come up with other methods that circumvent the speed of light limit, like warp drives. And what do? They're distorting the fabric of space and time and traveling and surfing that. We're traveling through wormholes. And these are all other ways you can get from A to B faster than a beam of light would have. But you're not actually moving through space faster than light to accomplish it.
So, like in Star Wars, which was, we're going to jump to, was it light speed?
Hyperspace.
Hyperspace.
Dude,
Hyperspace.
get your vocabulary.
Hyperspace. Is that plausible in some way? Like they've worked around?
Yeah, so because the future, so you give them whatever special engines they need, but they were distinguishing the fact that they can't just accelerate faster than the speed of light. Something has to happen okay, in order to engage that. And the streaking of the starlight, that's kind of what it might look like if you sort of did that. So I that's one of the 3 accurate things in the entire Star Wars series that is one can talk about that has any correspondence to physical reality.
The other is that Jar Jar Binks is a very good actor. That's another.
That's
I know a lot of people won't think.
Let me add that. That's the 4th thing, whatever.
There you go.
We got to take a break, but when we come back, more Cosmic Queries on StarTalk with my guest co-host, Paul Mecurio. We're back, StarTalk. Cosmic Queries, Grab Bag Edition. I got my guest co-host, Paul Mecurio. Paul, Mecurio, that feels like the planet Mercury, right? Is there an R in your last name?
There actually is. I had to change the spelling for performing purposes. My God-given name is Mercurio, or Mercurio.
God gave you that name. That's interesting.
He and we're like that. And,
you're on a last name basis with God, apparently.
Well, apparently I was born and a guy in a robe walked in and said, your name is Mercurio, and then they don't know if it was God or a homeless guy. But I'm going with God just so I feel important. And,
that works every time, yeah. Right. So you're born Mercurio, and you took it out. Why?
Well, I was had a part in a show in Los Angeles, and my manager called me and goes, "There's a problem." And I go, "What, am I getting fired from this acting job?" He goes, "No, but you will be." The real problem is that there's an actor in the union with the name Paul Mecurio, and I just was like, I went nuts. I'm like, what are the statistical chances of somebody having that same name? And it was this Australian actor. You may not remember him, but he was in this really good independent movie called Strictly Ballroom. He was I did see.
I was a ballroom dancer at the time. I saw that. Very interesting.
Oh, okay. And he was a great dancer. And apparently, the story there is he was a choreographer on the film, and the actor they hired really couldn't pull the dance moves off, so they put him in front of the camera, and he acted fine. And he had a career for a while, and he did Exit to Eden with Rosie O'Donnell and some other. So he got in the union before I did. So for a while, I was Paul Michael Mecurio. My confirmation name was my middle name, Michael.
You're so pious.
And
God gave you the last name, the confirmation. God gives you another name.
Hang on. Hang on. I got to heal a leper. Hold on one second. And get some water.
You had lepers in your apartment. Good. I'm not never visiting you.
Okay. It's my doorman. It's the best we could get with COVID. Everybody else is on unemployment. And so I tried 3 names for a while, and the end of the story is that God forbid somebody could introduce you and get Paul Michael Mecurio. They couldn't say 3 names and get it right, and so I dropped the first R in my name.
Okay, Mecurio. It worked. I got you. It was still good.
But I got Mercutio. I get references to Shakespeare. And I guess my name is sort of I have a tendency, I'm an Aries, so I don't know if you believe in astrology. But,
what do you think? Okay.
A little bit. And that I'm sort of a mercurial kind of human being. And my wife is easy. Very simple. Anyway, sorry. That was too long an answer. I apologize. You can edit all that out.
All right. So what do you have for the next question?
We're out of time. Thanks for tuning in, everybody.
Paul
David
took
Goldberg.
too long explaining
exactly.
the absence of an R in his name.
Exactly. In his head, Neil's going, why did I ask this moron this question? All right. David Goldberg, 2 parts. Hi, Dr. Tyson. We get it. You're a doctor. Back off. How do astronomers know how old stars are? That's the first question.
That's okay. Well, there's another part to that.
Yeah, I'll read it. I recently read that they observed a moon forming around a planet near a star that is only 6 million years old, and I was wondering how they can tell.
Yeah, okay. So that question is way deeper than most people know and imagine. So we look out in the universe, and how long are we alive? At most 100 years, and stars live billions of years. The universe has been around for 14 billion years. We're not sitting around and saying, there's one getting born, and there's adolescence, and then old age, and dying. We don't have that luxury. Right. All we can do is take snapshots. Okay? We take a snapshot over here, a snapshot over there, and we line it all up, and we scratch our heads. Okay? So now, by analogy, let's do the same for human beings. Okay, so let's say we are some insect that lives for 1 day. And we want to know, how do we decide how old humans are that we encounter? But we only live for 1 day. Okay, so I amass all of my fellow insects together. So let's take photos of humans throughout the day, bring them all back, and sit down and scratch our heads if the insect has a head. So what will they see? They will see a building with tiny humans in it. Okay? Very tiny.
How big is this insect? This is freaking me out.
Okay, I'm sorry.
Is it like a big praying mantis?
It wouldn't have to be an insect. Just another creature who's curious about humans as life forms the way we are curious about stars. Right. Okay? Mm-hmm. So they'll see women sort of facing this building with distended bellies. Okay? They'll see in the building, they'll see little humans, and then they'll also see women exiting the building holding these little humans. Okay, so that's kind of interesting. All right, hold on to that for a minute. They will see wooden boxes going into the ground. Okay? Oh, what's that? Okay. Oh, by the way, in the same building that has the women with distended bellies, they will see other humans laying down that are very wrinkled, maybe, or okay.
Do they see my super not fixing the leak under my sink? Do they see
yes,
that?
They will catch that as well.
And can they kill him for that? That's all I really care about at this point.
Okay. So you can ask, does this life form, are they born in the earth in boxes? Because you don't get to see the box move. These are snapshots, right? Right. And are like seeds, like plants, and we take them out of the ground, and they start out wrinkly, and then they get healthier and healthier, and then they begin to shrink and then disappear. Okay? Because you don't even know the time vector when you're just looking out in the universe. So you start assembling this, and once you bring enough of this data together, you can start constructing a timeline of a human being. And you might say, okay, here's another subtle point. You ready? Some people have this stick in their mouth and there's froth in their mouth. Okay? Not many. It's maybe 1 in 1,000. Okay? What fraction of a day are you brushing your teeth? Right? It's like a couple of minutes out of 24 hours. So most people will not be doing this. Some will be. So is it only this kind of person is only ever brushing their teeth and no one else does? Or does everyone brush their teeth?
It's like watching people running for exercise. These people are sort of, they're moving faster than most people are moving in terms of walking. What does this mean?
What does it mean? Exactly. Right? Or what, you won't see them moving. You'll just catch them with longer strides, in a long stride with wearing fewer clothes or something.
Like, wet from sweat, whatever that, yeah.
Right. Okay. So all of this has to go into a box. That you sit there and scratch your head, and it's like a puzzle, really. And you say, well, maybe this comes before that. Oh, we got this now. The distended bellies and this place and the women and do I even know that they're women? Well, statistically, they have longer hair, and so does everyone get a distended belly? So you have to think all of this through. For me, one of the more intriguing ones is trying to figure out whether one kind of person is the only one who's ever what you find in the bathroom, or does everyone go to the bathroom? You just didn't catch it because it doesn't take very long.
Okay,
because you'll just miss it. All right.
But you will be able to, of all this data that you're collecting, a very quick determination can be that there's only 2 types of these beings. A naked man looks one way, a naked woman looks another way.
Well, so but if you're a praying mantis, do you even see the difference? I mean, when you see a praying mantis, when you see a pigeon, are you saying, oh yeah, that's a female pigeon, that's a male pigeon? Well, you look really different. No, they can tell each other apart.
Well,
but can you?
When I look at pigeons, I try to look at them as more substantive beings. I'm not shallow like you. Like, hey, that pigeon's got a nice body.
Entire beings, right? So what may be obvious to us would be completely mysterious to another creature. You don't run around and judge the gender of goldfish, right? You have no clue because we don't have eyes for that. We don't. But
I'm not saying that they would say it's gender, but they'll start to see a pattern that there's these beings look one of 2 ways in terms of not size, not wrinkly,
but they do, but not all of them. Okay, so elementary school children, okay. Unless they're completely stripped down, they're just smaller humans, right?
Right.
And so the differences grow through middle school and high school, of course, but then you still have to figure that out. That's my only point. So fortunately, just for this visiting praying mantis or whatever creature it was, there are billions of people. Fortunately for astrophysicists, there are billions of stars. Because if you only do something 1 in a million times, and I have a billion of you out there, I will catch somebody in the act doing it every time.
Right.
All right? You need the large numbers to see the things that are rare. Okay?
And then to start finding a pattern through that data collection.
And to create the temporal nuances of what's happening simply from snapshots. So we look out in the universe and we say, there's a gas cloud over here. All right? And I see some stars deep within it. By the way, what are stars made of? They're made of gas. Maybe that's a stellar nursery. Because over here I see stars and there's no gas. So where did they come from? Wait, could it be that these stars dissolve themselves into a cloud? That could be. Maybe.
It's analogous to, are they born in these boxes and
in the boxes and come back out?
Come out reverse, or are they born and then, Okay.
Correct. So, so here's what you find. You ready? You keep doing this, and then you find out, wait a minute, this star just blew up. Oh my gosh, what kind of star is that? Oh, and you look very carefully, and we have other ways to determine it's a very high mass star. Only high mass stars blow up.
And then you can look at the fragments.
Okay, but wait a minute. So because you could ask, are they born with very high mass and then use up their mass over their lifetime and then just disappear? Right? That's another one, right? That's I start out big and I eat up my own flesh and I disappear. Right. But no, it turns out stars are born at a given mass. They use some of it during their life, but it's only a very small fraction of it, it turns out. And the high mass ones blow up with hardly any difference in their mass from when they were born. And the low mass ones never blow up. And they have a different color. And some stars never wander far from their birth, from their nursery. And you piece then you find out, there's a whole bunch of stars here that the gas is almost entirely dissipated. Now you can't make more stars, so they must all be the same age. Oh my gosh, and now I have a cluster of stars with the same birth date. Well, how about this other cluster over here? Well, the parameters are a little different. I see less gas among them, but these other things have changed. So maybe after 1 million years, after 1 billion years, these things are taking place. So this took decades with the most powerful telescopes in the world, and one of the leading telescopes was Mount Palomar in California. The Hale 200-inch telescope really put teeth in the stellar evolution understanding of this universe. So it was a very hard task. It took many brilliant people over many decades, not only the theorists to try to figure out what's happening inside the star that would cause it, but the observers who were saying, I see stars here, but not there. Okay? How come I don't see humans in the middle of the desert? Okay? And how come I see more humans where there's water? Oh, maybe you need water okay? Just keep doing it.
Right.
You keep doing it.
It's sort of this never ending.
It's a never ending thing. And the thing about the universe is, the bigger is your sample of stars, the greater is the chance you will see something that is so rare, it only happens once in 1 billion or 1 trillion times. Right? And so every now and then you'll see a headline saying, astrophysicists discover a new black hole that doesn't fit anybody's model or understanding. Well, because it's the millionth black hole we found, right? So, if I search enough people, I'll find somebody who has every disease you ever see advertised on television, right? Right? No, I'm serious.
No,
right?
No, I don't. Yeah.
Everybody's got, there's something, well, this is in 1 in 100,000 and 1 in 1 million, or what is it? Tay-Sachs? Yeah. Is it sickle cell? Is it?
It's my Aunt Christine. She's got every pain under the sun, my back, my head. No,
well, then she'd be a gold mine for the investigating aliens. Okay?
Good.
Because she's got all the data.
That's a perfect place to send her, actually. Let's put her on a ship. All right, we're going to wrap up on this. We got to take a break.
Oh, we got to take a break. Okay, damn, I'm taking so long to answer. Maybe we'll have a lightning round for the third period.
Absolutely. And we're going to be back right after this quick break.
We're back. StarTalk. I got my guest co-host, Paul Mecurio. Paul, how did people find you on the internet?
At Paul Mecurio.
No, that was a low-hanging fruit. You could say they find me repulsive. Paul, Paul, I don't want to be the teller of the jokes that are just dangling.
I forgot that you're so evil, and they find
I have bad breath. That's how they find me.
Yeah, they find me repulsive. That's actually a perfect way of describing me.
So Paul Mecurio on Twitter, is that?
Oh, you don't care, don't you? You just wanted to do
I want
this.
My people wanted to know how to find me.
Yes, at Paul Mecurio, Mecurio, 1 R, because we talked about this earlier. I had to drop the first R. And paulmecurio.com. And
that's one word, Paul Mecurio?
Mm-hmm. Paul Mecurio.
And Instagram or TikTok?
Instagram, Twitter, Facebook. I'm thinking about starting TikTok, but I don't know if it's...
TikTok is like a commitment. You got to be ready to get in on that.
Yeah, and I'm not... I got to dance, and I don't know. Nobody wants to see that.
Yeah, I saw you dance. You're correct. Nobody wants to see.
I didn't know you were a ballroom dancer. Is there anything you haven't done? This is amazing.
There's 2 things. Yeah, but no, I was on a competitive international Latin ballroom dance team.
Wow.
Yeah.
So you had
it was a team. So there were 8 of us, 8 couples, and it was the full choreography. It was
a good friend of ours does it, and she loves it, and she's in great shape from it too. It's amazing.
Yeah, and that movie came out right at that time, and so it was field trip for the dance group. So what do you have? You got questions?
We're going to jump back in. Yeah, we have a question from Toby.
Wait. Did I finish the second half of that question? Because we found a moon orbiting a planet, orbiting a star. So what we find is the stars that are being born in these gas clouds, we also see disks of material. And then we say to ourselves, could these disks of material be the proto-material that will then make planets in orbit around this star? And so sure enough, this is what we observe. So yeah. And so you can observe planets forming around stars. And then the planets themselves, some of them have disks. And out of that disk, they would have their own moon. So it's pretty cool.
Can I ask a quick follow-up on something you said in the last segment?
No, unless you're a Patreon member. You can't.
Okay. All right, here we go. Okay, Toby Sonnenberg. Hi, Neil. Could you please explain what the crisis in cosmology is? What are some possible ways the crisis can be resolved? What do you think is the most likely resolution?
Oh, this person's doing some homework there. Okay. Well, so old timers, it's hard to call it a crisis. It is a crisis, but for old timers, it's really hard. All right. I'm an old timer. I come from an era, an epoch, okay, where we didn't know the age or the size of the universe, because they're related, to within a factor of 2. Okay? A factor of 2. Is the universe 10 billion years old, or is it 20 billion years old? And if you put all the data together, people sort of picked and chose and sifted, and there was the 10 billion year camp and the 20 billion year camp, and they were warring factions for many years.
But there are two methodologies to...
That's right. So the methods are different. The chosen objects
cosmic microwave
are different. So this is how you get this divide, and it's on the frontier. And eventually, with better telescopes, better data, which is how this is always solved. All right. That's the good thing about being a scientist. You can get into a fight, and in the end, you both agree. It's an unwritten contract that you and I have that either you're right and I'm wrong, I'm right and you're wrong, or we're both wrong. And they'll reach a point where we say, we need better data. Let's go have a beer. Okay. So that's how that works. Right. There's no duel. There's no who shouts the loudest. That's not how we roll. So, but there's
an analysis that looks at sort of historic data, and then there's one that looks at sort of current state of things. And
there's another one that says, here's instructions for the next wave of observations. I need you to look at it this way because that'll help me resolve this uncertainty. So with this factor of 2 warring factions, with new data, especially with the Hubble telescope and the observations of the cosmic microwave background with 3 satellites that were engaged in this, one successively more precise than the next, so it turned out the uncertainty was no longer a factor of 2. It narrowed. And of course, the actual answer ended up somewhere in between. All right. So we're now at about 14 billion years. No one is saying 10 or 20 anymore. All right. So you'd expect that. If the 2 warring factions, the right answer is probably somewhere in between, as it turned out to be. All right. So we're all happy, 14 billion year old universe. And then people start looking more carefully at it. They use this method and that method, and our observations are so precise. People are saying, and I forgot the exact 2 numbers. Is it 14.0 and 14.6? There are 2 different ages.
Well, it says the crux of the disagreement is at 67.4 plus or minus 0.5.
That's the value of the Hubble constant, which then gives you the age of the universe. Okay. So give me those 2 numbers. That's fine. 67 and the other number?
67.4 plus or minus 0.5 and 73.2 plus or minus 1.3.
So these 2 numbers
kilometers per second per megaparsec.
Megaparsec, right. So those 2 numbers are the fabled Hubble constant. And you use the Hubble constant to get the age of the universe. I was content giving this answer in the context of the age of the universe, but now you threw in the Hubble constant in units of kilometers per second per megaparsec.
Because clearly you don't want to do your job thoroughly, and I'm covering your behind. Like, I got to carry you. Go ahead, Mister. I know the universe. Go ahead.
So the Hubble constant version of the age of the universe is the Hubble constant 50 or is it 100? Okay, That gets you these two different ages of the universe. All right. If the Hubble constant is 50, then the age of the universe is 20 billion years. If the Hubble constant is 100, then the age of the universe is 10 billion years. So, but point is, if you want to speak in Hubble, if you want to be Hubble constant fluent, that's fine. Those two numbers, which used to have a huge uncertainty, no longer has a huge uncertainty, but now they each have their own camps because the uncertainty in each number excludes the other number. Okay, so we measure those two numbers so precisely that the 73 doesn't allow the 67 in its error bars in the range of uncertainty. You know, the uncertainty when you read election polls. Yeah, they're leading by 60%, plus or minus 3%. Okay, that's an uncertainty where the data can't distinguish. So if you put the uncertainties around those two numbers, the uncertainties don't overlap. So that's a crisis in cosmology.
Well, what camp are you in?
And I'm just saying, to call that a crisis, what a luxury of precision measurement.
Right. You would prefer the crisis because you as a scientist like the challenge of trying to figure things out and come to resolution. And this is a challenge still for you. And
when you have a crisis, it energizes people. That's correct. And we call it a crisis because those two numbers had uncertainties that overlapped, then it's just a matter of time you get some better data. It might be that these two methods, because it uses different methods to
Can you just hit on that for a second? I mean, maybe everybody listening knows, but like, in which method do you subscribe to? Because
I have no such investment in my emotional energy. I step back and I embrace it all.
Wow, this got really esoteric. And can I have some of what you're smoking in the break? Because that was a pretty awesome answer, man.
No, it'd be something like you want to measure the length of the length of some object, and one person pulls out their pocket ruler and they do it. Another person pulls out a laser, and another person pulls out like an inchworm. Okay, and then they get three different results.
Right.
But every time they repeat it, they get approximately the same results, and the results don't agree with each other.
Right.
So you have to say to yourself, one of these results is wrong, or maybe the inchworm is relativistically effective. I don't know. You have to, okay. It could force another understanding of the world.
A third measurement. I mean, they both seem valid. I mean, one is when the universe began, and then using theories to predict today's expansion rate.
They're completely valid, and that's why we're scratching our heads. Or they are irreconcilable, and there's new physics that we need to put on the table that tells us why. We all love new physics because it's like you broke through a door, and on the other side of that door is this beam of knowledge and wisdom that could shed light on other stuff that still has you scratching your head. And let me give an obscure example of this. We have what are called GPS satellites. You've heard of them. Mm-hmm. And they orbit. They're in a place in Earth's gravity field where their clocks tick faster than our clocks. Okay, all according to relativity. If Einstein's relativity had not yet been discovered, and we launched these satellites for the sole purpose of establishing a coordinate grid on Earth where timing is essential, we would see that it would constantly be sending us time that's too fast. And we'd say, engineers, what did you design? You must have made a mistake. Go back to the circuit board. Go fix it. Check your drawings. We would first assume that there was some mechanical problem with it. And the engineers say, no, here's the twin of it on Earth, and no. So, well, what's going on? We can't figure it out. And so that would be a dilemma. And then Einstein would come along and say, we have the general theory of relativity that's explained trivially. Bada bing, a whole new field of physics opens up. So most crises in science lead, I hate the word crises because that implies human.
Yeah, exactly.
Dilemma. How about dilemma? How about that? Okay. Most dilemmas,
the challenge
is in science lead to new physics. Yeah, breakthroughs. Right. There you go. Yeah. So that's the whole story there.
Yeah. Well, I knew that. I just didn't want to say anything. All right, we're
Let's do lightning round. Yeah.
We're going to do lightning round. Okay. So we got some really great questions that we want to get to.
I'm taking too long to answer these.
No, you're not. It's always interesting. I fall asleep in the middle, but then I wake up. All right. Peter Jacobs.
While I'm facing the chalkboard, that's when you catch up on your notes, on your reading, and on your
shooting spitballs at your back of your neck. Peter Jacobs, he's got two questions. Let's do the first one. If two black holes collide, can we tell their relative relations with LIGO, and how do they affect the final rotation of the resultant black hole?
Excellent. So this is lightning round. So LIGO, the Laser Interferometry Gravitational Wave Observatory, is exquisitely tuned to look at the ripples through the fabric of space and time, predicted by Einstein in his general theory of relativity, that when you have a gravitational disturbance in the space-time continuum, it sends a ripple moving at the speed of light. And two colliding black holes will do that. Before they built LIGO, they set up models of what all manner of black hole collisions would look like. Equal mass, very different mass, slightly different mass.
But what was the basis for the models? I'm not making a joke. Is this analogous to sort of this praying mantis taking a snapshot of us on Earth and putting together?
Yeah, because we're not going to have a million examples here. So you want to set up a catalog that, because you know general relativity, it works. We know black holes. We think we know what will happen when they collide. And so we say, okay, here is the gravitational wave signature that we just measured. Let's hold that up to our catalog. And which one does it come closest to? There it is, a 30 solar mass black hole and a 15 solar mass black hole. There you have it. Now, depending on how far away they were when they started their spiral, they have what's called angular momentum. And this is the momentum of rotation. And that some of that angular momentum is carried away. But I don't know if it's most, but much of it remains within the system, and you have a rotating black hole. So black holes rotate too, just like everybody else.
Okay, we're going to get to the next one. Thomas Yu.
No, he had a second question, you said.
He did. Oh, okay. I was just trying to get to everybody, so I figured
let's do it.
First. Okay. Why bother sending a probe to another star when it will most likely find one we sent later? Isn't that statistically unlikely, though?
I think he meant the opposite of that. I think what he might be saying is, if you send a probe to another, and I don't want to invent a question that he's not thinking, but here's a version of that he might mean. You send a probe to another star, it'll take 50 years, or even okay. But in those 50 years, we invent a way to tunnel or wormhole to the star. And so you get there faster than that would have ever arrived, because when we sent it, we didn't have that technology yet.
But it developed.
And so there it is, just passing it by and saying hello.
Hey, Damicia.
Right. So people have argued, why don't we wait until the technology is better and then do it right?
To send a probe to right. But
correct.
But it's not like we're doing it wrong. Is that? I mean, that sort of presupposes that we're getting information that's inaccurate, or
no. It's just why bother, right? If you're going to say, if you're in California and you say, we discovered gold, put the notice on the back of a tortoise, okay, and send it back east. You can say, no, let's wait until the railroad is built, or well, let's wait until
right. Let's make it a little bit
pass the turtle in St. Louis. We'll get it'll be better. Okay. I think that might be what he means. But okay, keep going.
Right. Thomas Yu, hello team. Has anyone tried to calculate the cost and natural resources of planet Earth if SpaceX would follow through with the plans to colonize Mars?
So that implies that the colonization of Mars requires taking natural resources from Earth to put it there. But if you're going to colonize, the way to do it is, you do everything in situ. Okay? This is the buzzword, in situ resource utilization, ISRU. Google it. Okay, and NASA has full running pages. When you get to a destination, dig in the soils, get the carbon dioxide, split it, get the water, split the water molecule. You get oxygen, you can breathe it. The hydrogen, you get a rocket fuel. All of this is what
Martian,
you would do.
the movie, 2 hours. Martian.
Thank you.
Hello.
Hello.
Do we need anything else to be? Matt Damon, the most brilliant, second most brilliant next to Neil deGrasse Tyson, man in the world. Anyway, go ahead.
So ideally, that's what you would do. Otherwise, no, I don't. Whatever they had to take to have lunch for a year, that's not going to throw Earth off its axis. So don't worry about that.
A lot of Subway sandwiches, that kind of thing. Real quick, we have to wrap up. I mean, what are some of the advantages of colonizing Mars?
Well, if an asteroid takes out Earth, then humans don't go completely extinct.
Okay.
But
that's a very negative attitude. How about
it's negative attitude. No, I'm a contrarian there. I don't even agree that that's why you should do it. So we have more eggs in more than one basket. If you have the technology to go to Mars, terraform it, colonize it with 1 billion people, it seems to me you have the technology to deflect that asteroid that's headed for Earth.
Yes,
okay?
Yes.
Oh, we're destroying Earth with global warming and the billionaires are all escaping and they're going to form another planet and then they're going to terraform that planet because Elon is into terraforming. It seems to me if we have the power to terraform Mars
redirect the focus
into Earth, then we have the power to turn Earth back into Earth.
Yes.
Okay. So
said.
Don't worry, we're cool here.
All right.
One last question. Let's slip it in.
Want to slip one more in? Okay. This is Alexander Wisnent. If gravity is due to mass and acceleration, could we get an object with enough gravity to pull something at the speed of light?
If you fall into a black hole, basically you come near the speed of light as you come near. And what happens is as you come near the speed of light, it's harder to distinguish you as a blob of mass from you of what would then become a blob of energy. So the mass energy equation very much favors the conversion of matter into energy. And so yes is the answer. And that happens in black holes all the time. And if you don't believe me, try it. Call me up and tell me how it goes.
Hey, Neil, I'm falling through a black hole. Oh,
just like you said.
I think you're breaking up a little. Oh, my God. I'm breaking up.
Wait, can you hear me now? Wait, let me go to another part.
This was not a good idea. And then Neil makes some notes and moves on with no emotionality about it at all. We are done. We've got more to go.
Thanks for coming in for this.
Yeah, this is so fun. And
it's good to see you again. I hadn't seen you in a couple of years. Nice to know you're still out there and and holding down the Colbert for it.
Absolutely. Are you going to be back on soon? We got to get love to
on
see
Colbert.
I
got to write another book to get back on. I got to earn it. You know.
All right. Okay.
That's what that is.
Let me put a word in for you. I know this up and coming scientist. You might have heard him. He's got a thing or two. Thanks. This is always great. It's always
By the way, you know what I said?
This.
I was on his show March 2020, like March 9th. All right. It was like the last week that he
You're the reason COVID shut everything down.
And he says, what do you think of this COVID thing? And all I said was, it is an experiment in whether humans will heed the advice of science and medical professionals.
Right. And
that's
we
what
failed.
I said. Okay, that's all I said.
And we're continuing
this is
to
an
fail. But
experiment.
that's a show, a show for another day. But yeah, that's a really great answer, and you hit it on the head.
What it is.
This is the show.
We out. Thanks, Paul. This has been StarTalk, Cosmic Queries Edition. And I've been your host, Neil deGrasse Tyson, as always, bidding you to keep looking up.